last time we have seen a composite a rectangle rule, composite midpoint rule, and we have seen that whenever you are going from basic rule to composite rule, there is a loss of 1 power of h. Okay, and not only with the midpoint rule and rectangle rule, it is also we have seen with the trapezoidal rule and Simpson's rule as well. Okay, so let me write some comparison here that if you use the rule, so let's have this, let's take the name the rule, and the first rule is, let's say, rectangle rule. Another rule is what's midpoint rule, and what other rule we have learned is trapezoidal rule. And then we have learned the Simpsons. Simpsons indeed is called as Simpsons 1/3 rule. Okay, right. Now, if you take, so what is the degree of interpolating polynomial we have used in each case? Degree of interpolating polynomial. So in the rectangle rule, we have taken a constant polynomial, 0 degree, means 0 degree. In midpoint rule, we have we have interpolated a constant polynomial, and in trapezoidal we have taken the linear polynomial, this interpolating polynomial, and in Simpsons we have fitted the function by a quadratic curve, so with an interpolating polynomial too. And what we have got is the exactness of these is achieved. So exact for polynomials of degree is the rectangle polynomial is exact only for the constant degree polynomial. Other for midpoint rule, what we have is we have taken the interpolating polynomial as a constant polynomial, but we got it exact for 1 degree polynomial, up to degree polynomial of degree less than equals to 1. And for trapezoidal rule, we have had exact for polynomial of degree 1, because if you look at the error term, they are involving second derivative. And in this rule, we have seen that we have taken degree of interpolating polynomial is 2, and we get the exactness for polynomial of degree less than and equals to 3. Now, to achieve this, what is the smoothness required? I just want to compare here smoothness of the function in the error term. So here the C1, the C1, one-time differentiability. Yeah, midpoint rule, we have got the second derivative right in the error term, so it is required C2. In trapezoidal rule, it is also required C2, the smoothness. And the Simpsons rule, in the error term, you have seen that this is going to be 4th order derivative here, so it requires C4. So function needs to be 4-time differentiable. And what is the order of h? You can say what is the order of convergence we have seen here. So order of convergence in each case, if I look at here, that was here, you have this is OH, this is OH square, and trapezoidal rule, what we had is, so what you have here is of h square, and this is of h to the power 2. Means order of convergence here is 1, linear convergence. Order of convergence is 2 in the both cases. Okay, now if you compare, let's say the you have this column here. Let me add one more column. How many number of function evaluations required in each case? Okay, number of functions evaluation. Number of function evaluation in each case. In the rectangle rule, how many number of functions are required are n, right? Because it's taking a number of functions f of x naught, f of x1, and so on, f of xn minus 1. So you are taking left end point of each subinterval. Okay, so in the rectangle rule, so the number of function evaluations are n in the rectangle rule. In the midpoint rule, you have the number of function evaluation is n. In the midpoint rule also, because you have taken the midpoint in each subinterval, so there are n number of subintervals, so the number of function evaluation is n. For trapezoidal rule, you you have left hand point and right hand point both. But if you go, this left the right, so if you start with x naught, x1, and so on xn, so you are going to evaluate function at each point, so n plus 1 points. Okay, and what about Simpson's rule? So in the Simpson's rules, you are taking everywhere in every midpoint of the interval also. So n number of n plus 1. So that is going to be 2n plus 1. Now see, look at here. So midpoint rule and trapezoidal rule, they are they are very close. So here is you have taken the degree of interpolating polynomial, you have taken constant polynomial, and this you have found it exact for polynomial of degree less than equals to 1. Similarly for trapezoidal as well. And in the both the case, order of convergence is same. And function number of function evaluation is n and n plus 1. That is, there is not much difference, because if you go for large enough n and n plus 1 are almost the same now. Okay, right? Now, however, if you are going to, if you wish to go for order of convergence 4, then you have to go for this. You require the smoothness C4, okay, and you require the number of function evaluation is 2n. Now we are going to use the cubic Hermite interpolating polynomial to create one more quadrature rule, numerical quadrature rule, which is known as a corrected trapezoidal rule. So we are going to use now cubic Hermite interpolating polynomial. Okay, we are going to use this for approximating the function f. Okay, now if you recall, from your previous lectures, you have defined x naught equals to x1 equals to a, and x2 equals to x3 equals to b, and you require the function derivative values f dash a at n, f dash at b. And if I recall, the cubic Hermite interpolating polynomial was p3 of x. I'm just writing straightforward. You can refer the lecture. Is equals to f at a plus the divided difference f a times x minus a plus f at a b x minus a square plus f a b b times x minus a whole square times x minus b. This one. Now this is going to be a cubic Hermite interpolating polynomial. Okay. Now if you perform, so if you approximate, so if we approximate, or you can say replace, okay, approximate f of x by this p3 of x, cubic Hermite interpolating polynomial. Okay, then your quadrature rule, so integration a to b f of x dx is approximately equals to integration a to b p3 of x dx. Okay, now Then if you perform the integration here, so f of a is going to be replaced by f dash of a. Okay, and f db is going to be f dash of b. Okay, and if you perform the integration here, term-wise integration, okay, I'm going to write the simplified form here. So what you will get is equals to b minus a by 2 times f of a plus f of b plus b minus a whole square by 12 times f dash at a minus f dash at b. So if you have prior values of f dash at its endpoint as well, along with this, then you can actually achieve the order of convergence here is means it will be exact for polynomial of degree less than equals to 3. Okay, and suppose your function is periodic. Okay, and its derivative is also periodic with length b minus within the length of the interval b minus a. Okay, then f dash of a is equals to f dash of b, and then it will reduce to a simple trapezoidal rule only. So this is nothing but if you look at the first term here, this is nothing but the basic trapezoidal rule what we have learned previously. So if the function is periodic, okay, and its derivative is also periodic with period of the period b minus a. Okay, then it's this f dash of a is equals to f dash of b, and then you have this is equals to 0. This quantity will not contribute anything, and you have the this trapezoidal rule approximation is going to be given by the trapezoidal rule, and which gives you the exactness of polynomial of degree less than equals to 3. Okay, so you can work out with the error term as well here. Okay, so if you look at the error term, so error is equals to integration a to b f of a b x and x minus a whole square into x minus b whole square dx. Now you can apply the mean value theorem here, right? Because this will always be greater than equals to this does not change sign, and so and if you assume that it is going to be 4 differentiable f, okay, then it will assure the continuity of this divided difference, and that is going to be given by f fourth derivative at some d by 4 factorial time integration a to b, this one a to b x minus a whole square times x minus b whole square dx. And now if you simplify it, that it's going to like the final term f fourth derivative at t divided by 720 times b minus a to the power 5. Now if you go with so b minus a that is what is h here is v minus a. So when you apply the this corrected trapezoidal rule, so this above is known as corrected trapezoidal rule. If you apply in the composite one, you will reduce one power here. So what you are expecting is of h4. So in the composite rule, so this is going to be of, you can say h to the power 5. In composite rule, error we are going to see as big of h to the power 4. So now we can go back and update our table now. Okay, and we can look at the corrected trapezoidal rule. Okay, so we can fix now here. You can say corrected trapezoidal rule. So degree of interpolating polynomial is 3. Exact for polynomial of degree 3. It also assumes the smoothness 4, and you obtain the order of convergence is OH to the 4. So where will be the big difference here? It is going to be, see, when you are going to apply the composite trapezoidal rule, corrected trapezoidal rule here, see, these are sitting with the negative sign. And when you open it up over xi to xi plus 1, then all other terms will get cancelled. Only will survive is f dash a minus f dash of b. Okay, right? So this will be remaining the same. Okay, right? So you only require these two number of derivative. Instead of that, you don't require here the derivative values at the interior points. So for the composite trapezoidal rule, if I say here, so you require the functions values at x0, x1, and so on, xn. x0 is equals to a, xn equals to b, and xn minus 1, x1, x2, and so on. So you require the function values as these points, but because of this difference here, when you apply here summation, so if you look at so integration a to b f of x dx is approximately summation I equals to 0 to n minus 1 integration xi to xi plus 1 f of x dx, this is exact, equal to, now you replace it by interpolating polynomial, so summation I equals to 0 to n minus 1. So you have xi plus 1 minus xi by 2 time f at xi plus f at xi plus 1, this one, plus xi plus 1 minus xi square by 12 time f dash at xi minus f dash at xi plus 1. Now, if you open up this bracket, all the intermediate values of the function of f dash at x1, x2, xn minus 1, all will get cancelled because of this negative sign. Only will survive is the first term, which involve the functions of x1, x0 to xn, and the second term will be this is going to be xi plus 1 minus xi is h square by 12 time f dash of a minus f dash of b. So how many number of function evaluation is there? So that is going to be here n plus 1, and here is plus 1 and plus 1. So n plus 1 plus 2. So number of function evaluation in here is going to be n plus 3. So if you want to achieve the order of convergence 4, and if you have the same smoothness, and which you can get by number of function evaluation by now as n plus 3. Okay, then you will achieve the same as Simpson's rule. Okay, then Simpson's rule and corrected trapezoidal rule are at the same point. Okay, right. So earlier what we were doing is by deriving these rules, Simpson's rule, trapezoidal rules, and so on. Okay, so what we were doing previously, we are fixing interpolation points x0, x1, x2, xn, and then approximate f by an interpolating polynomial Pn of x plus some error term. And then we are going to get integration a to b f of x dx is by summation I is equals to 0 to n wi f of xi, where wi was, if you recall, is going to be integration a to b li of x dx. Okay, now we are going to look in the reverse way. can be means like we are fixing first x naught x1 x2. Now what we are going to now do is we are going to seek a new formula. Okay, so we seek a formula integration a to b f of x dx is summation I equals to 0 to n wi f of xi. We seek a formula this, we will call this as 1, where we wish to determine wi and xi. So we are not fixing at the first hand itself. So we are going to determine wi and xi so that the one is exact for polynomial of degree as high as possible. Okay, so how many number of unknowns are there? W0, W1, W2, Wn, X0, X1, X2, Xn. So there are 2n plus 2 unknowns. So what we can expect is, we can expect the polynomial, the formula 1 is exact for polynomial of degree 2n plus 1, less than equals to 2n plus 1. Okay, since there are 2n plus 2 unknowns, which we are going to, so w xi, so that 1 is exact for polynomials of degree as high as possible, we may hope to get one which is exact for polynomials of degree less than equals to 2n plus 1. Now, if you look at the basis of this, for the set of polynomials of degree less than equals to 2n plus 1, if you recall, what will be the basis is 1 x square to x to the power 2n plus 1. Now, means if the formula 1 is exact for these polynomials 1 x square and so on x to the power 2n plus 1, the span of this will lead you to for any polynomial of degree less than equals to 2n plus 1. So this side. Okay. So if the 1 is exact for each individual of this set, then it's going to be exact for polynomial of degree less than equals to 2n plus 1. Now, note that there are 2n plus 2 unknowns. Now, if you substitute f of x equals to 1, you will have first equation. F of x equals to x, you will have second equation. If you have to substitute f of x equals to x square, it will give you third equation, and so on. So if you substitute x to the power 2n plus 1 there, then it is going to be give you the 2n plus 2 2th equation. So there are 2n plus unknowns, and you have 2n plus 2 equations, which is, and they are on the basis here. So that will give you the unique solution for them, and you can find all the possible unknowns. So let's look at the special cases now. So let's look at the special case. Special cases, let's say n equals to 0. Means now we wish to determine x0 and w0 so that the 1 is exact for polynomial of degree less than equals to 1. You replace n equals to 0, we are expecting is less than equals to 1. So you are going to use 1 comma x as a basis. So you are going to use f of x equals to 1 and you are going to use f of x equals to x, substitute, and then you get back the w naught and x naught from there. Okay, right. So we seek is integration a to b f of x dx is equals to w0 f of x0. So that is exact for polynomials of degree less than equals to 1. So when f of x should be exact for constant, so f of x equals to 1 should be exact for this. A to b dx is equals to w naught. F of x0 is also 1 because f of x is constant. So this will implies w0 is equals to b minus a. Now the second condition, f of x equals to x, it should be also exact for this. So what you will have, integration a to b x dx is equals to w naught. F of x naught is x naught. This will imply, but w naught value is b minus a time x naught is equals to the left hand side. If you evaluate x square by 2, upper limit minus lower limit, that is b square minus a square by 2. Now b minus a will get cancelled on this side. So what will give you is x naught is nothing but the midpoint of. So the formula is what? Integration a to b f of x dx is equals to b minus a time f at a plus b by 2. And which you already see, okay, previously. And this is nothing but the midpoint rule. Okay, and you can talk about the error in the similar. Okay, error form is already given to you so that we can look at. Okay, right. Now the next special case we are going to take is n equals to 1. So now the next case we are going to take n equals to 1. Means we wish to determine x naught, x1, w naught, w1, 4 constants, which is exact for polynomial of degree less than equals to 2 into 1 plus 1. So that is equals to 3. So less than equals to 3. We are looking for polynomial. The formula should be exact for polynomial of degree less than equals to 3. So your formula is integration a to b f of x dx is approximated by summation I equals to 0 to 1. So instead of this, we are going to write w0 f at x0 plus w1 f at x1 exact for polynomials of degree less than equals to c. Therefore, exact for the polynomials f of x equals to 1, x, x square, and x cube. So we are going to substitute one by one and we will get 4 equations in 4 unknowns. So now f of x equals to 1 gives naught plus w1. That's very straightforward. That is integration a to b. F of x is 1. Integration a to b dx is going to be b minus a. F of x naught is also 1. F of x1 is 1. F of x equals to x. So what it will give you is, so w naught x naught plus w1 x1 is equal to b x dx. So that is equals to b square minus a square by 2. Now similarly f of x equals to x square. What it will give you is w naught x naught square plus w1 x1 square is equals to integration a to b x square dx. So x square integration x cube by 3, upper limit minus lower limit b cube minus a cube by 3, and f of x equals to x cube implies w naught x naught cube plus w1 x1 cube is equals to integration a to b x cube dx. So integration of x cube is x to the power 4 by 4. So that's going to be b4 minus a to the power 4 by 4. So you have equation that is displaced in 2, 3, 4. So you have 4 equations in 4 unknowns now. Okay, which you can solve and you can get it back. So what are the values of w0, x0, x1 and w. But look at here, they are not linear equations. Okay, you have to do some manipulation here. You replace w0 by b minus a minus w1 and try to reduce the number of constants in other and try to solve that. So you do some manipulation here and try to get these x0, x1, x2, sorry, x0, x1 and w0, w1. So if they were the linear equation, we could have solved by using this LU decomposition method or so. Okay, right. So still you can deal with this case by doing some manipulation. But we wish to determine a procedure which is applicable for the general case, which like n equals to k. We are going to use now inner product spaces. You have learned already during linear algebra inner product spaces on the space of all continuous functions that we are going to take here. And also we are going to recall the Gram-Schmidt orthonormalization process. Okay, that will come into the picture now. Okay, so what we wish to determine x0, x1, w0, w1. Okay, so we have to interpolate by a polynomial, okay, which actually leads to the formula to be exact for polynomial of degree less than equals to 3. So with the 2 points, you can go with at most linear polynomial, right? Okay. Now here you will get it. So we are going to choose now. So we are going to take different procedure for obtaining these x0, x1, w0, w1 values. And then we can directly link to the general case. Okay. And then we will able to define the this Gaussian quadrature rule for the general case. Okay, right. So now we choose x0 and x1 so that the error in fitted linear interpolating polynomial is 0. Okay, we choose x0 and x1 so that the error in fitted linear interpolating polynomial is 0 for polynomials of degree less than equals to 3. Means for polynomials of degree 2, for polynomial of degree 1, for polynomial of degree 3, if you are going to apply the corresponding interpolating polynomial over there, then there should not be any exact for the quadrature rule. Okay, so whenever integrate less than equals to 3, whenever integrated over closed interval AB. Now, so let's look here. So we are going to approximate f of x. So by linear polynomial, so that's going to be f of x naught plus f of x naught comma x1 time x minus x naught. This is your linear polynomial and plus the error term x naught x1 comma w of x. What is w of x? Is x minus x naught into x minus x1. Okay, wx is nothing but x minus x naught into x minus x1. So this implies integration a to b f of x dx is equals to integration a to b this p1 of x dx, which you can integrate easily, plus this error in this integration a to b f of x naught, x1, x, and wx, that is x minus x naught into x minus x1. Now we are going to work out with this. Okay, right. So we are going to see what had happened in during midpoint rule and Simpson's rule. Now what happened that integral w of x dx was 0. Okay, there when you consider the quadratic interpolating polynomial, then you have that interpolating polynomial. Then you had seen that integration a to b integration a to b x minus a into x minus a plus b by 2 into x minus b dx is going to be 0. Okay, so we are going to use the fact that, okay, here means, or in other words, we are going to follow the similar procedure here. Okay, right. So now we are going to look at this. We have this error is integration a to b f at x naught, x1, x time x minus x naught and x minus x1 dx. So not that x naught and x1 are any points in between the interval a to b. These we have to choose. Now, if x naught and x1 are so that the integration a to b x minus x naught into x minus x1 is 0. Okay, so which is wx. Okay, now let's say we are going to assume that x naught and x1 such that, because they are in your hand, integration a to b w of x dx is 0. Okay, then how will you utilize this in the previous term? So now I can rewrite f of x naught comma x1 comma x as follows using the recurrence relation. That's going to be f of y naught, x naught, x1. I'm introducing one more point here. F of y naught, x naught, x1, comma x time x minus y naught. Now you can see, you can send this on this side, and you can look at here that x minus y naught will be in the denominator for this recurrence formula. Okay, so y naught is a fixed point. So here y naught is fixed point. It's not a variable. Y naught is fixed point that we will choose later comfortably. Okay, like we have choose there that the c is equals to a plus b by 2. Okay, so similarly we are going to make them in choice. Okay, make its choice here. Now if this is there, so we are going to write here then, and if we have assumed that x0 and x1 are such that integration a to b wx dx is 0, so you multiply by wx and then integrate. So then what will be the error is, so integration a to b over here, so this is a constant, this will be out, so you have integration a to b of x dx is 0, right? So this term will not contribute anything, the first term will not contribute anything in the integral. So this is going to be, I'm just writing integration a to b f of y naught x1 w of x dx plus integration a to b f of y naught x1 x minus y naught into w of x dx. Now since this is constant, this is out, so this is going to be, first term is going to be 0 because x0 and x1 are such that integration a to b w of x dx is 0. Now this is equals to integration a to b f of y naught x1 x w of x time x minus y naught dx. Now what you can do next here? Now see, if you remain here, so this is using 4 points, and suppose this does not change the sign. Okay, then you apply the mean value theorem, and you will get this 4 points of third order derivative, and you get the exactness till second degree polynomial. But you wish to go for up to third degree, 3 degree polynomial. Okay, so again we are going to use a similar type of recurrence relation here, and assume that x0 and x1 are such that this integral a to b w of x times x minus y0 is 0. Whether such things are possible or not, that we will answer later. Okay, right. So now assume that x0 and x1 are such that integration a to b w of x times x minus y0 dx is equals to 0. Then what will happen? You again apply the similar recurrence relation, means it will include one more point, say y1. So what will be? Now you can write f of y0 comma x0 comma x1 comma x as f of y1 comma y0 x0 x1 plus f of y1 y0 x0 x1 x times x minus y1. So again y1 is fixed now. So if then because of the previous assumption, so you multiply by w of x into x minus y0 and then integrate. So then this implies, so integration a to b, so error term is equals to integration a to b. So first term contribute anything because of the previous assumptions. So error is equals to f of y1 y0 x0 x1 x times w of x times x minus y0 times x minus y1 dx. You can again look at first term will not contribute anything. Okay, now if provided this is provided integration a to b w of x dx is 0 and integration a to b w of x times x minus y0 dx is 0. So these are the assumptions. Okay, provided these conditions are satisfied. So then only this case possible. Now let y0 is equals to x0 and y1 equals to x1. So choose x0 and x1 and with y0 and y1 also as same as x0 and x1. Then error is equals to integration a to b f of x0 x0 y0 x1 x1 x and w of x was x minus x0 x minus x1. This is x minus x0 into x minus x1. So you will have x minus x0 square and x minus into x minus x1 square dx. Now see, this will not change sign because this always remain positive, and you can apply the intermediate value theorem for this case. By assuming the differentiability of function, smoothness is required for fourth till fourth derivative. So if you apply mean value theorem, so mean value theorem implies that error is equals to a fourth derivative at some b by 4 factorial integration a to b x minus x naught square times x minus x1 square. So we have obtained mean value theorem implies this. So this is only possible. So this will give you the guarantee that the above formula will remain exact till polynomial of degree less than equals to 3 because of the fourth degree there. This is going to be constant number, some C. Okay, we are going to see later. Okay, so this gives you guarantee that such formula is obtained provided you have the conditions. So one condition is integration a to b x minus x naught into x minus x1 dx is 0. Okay, another condition is integration a to b x minus x naught into x minus x1 into x minus y naught was x naught square dx is 0. Now if you are going to split this x minus x into x minus, so I'm just going to, so this is nothing but the w of x. Okay, so this is w of x. So instead of we are going to, so x is a constant, so means integration a to b w of x dx is 0 and integration a to b w of x times x minus x naught is 0. Now since if you open it up, so it's going to be integration a to b, so I'm going to write integration a to b w of x times x dx minus x naught times integration a to w of x. But since wx dx is already 0, this will not contribute. So instead of means one more x minus x naught factor, what we are going to look at here is the conditions are integration a to b w of x dx is 0 and integration a to b w of x times x dx is 0. Okay, now we are going to look at it now more carefully. Okay, because we want to go for, so this x0 and x1 can be chosen in this fashion. So you can solve these two equations and you can choose those x0 and x1 from here. Okay, but we want to, again I'm mentioning, we want to have a general procedure. Okay, so we are just going to suspend this for a moment. So we are going to come back here. What will be the values of x0 and x1? Okay, by recalling some preliminaries, you can. Okay, right. So let's say now in order to find the general procedure, so we recall inner product spaces. Inner product space and CAP. And how the inner product is defined here, f comma g, inner product is defined by integration a to b f of x times g of x dx. Okay, now you can recall that when you will say such type of relation or function will define the inner product. So you have properties are f comma f is greater than equals to 0 and f comma f is equals to 0 if and only if f is equals to 0. Second, if I recall, that's going to be let's say f comma g plus h is going to be f comma g, means linearity, f comma g plus f comma h. So linear with respect to first variable, linear with respect to second variable as well. Okay, right. Third, alpha f comma g is going to be alpha times f comma g. Okay, and fourth is we are talking about only on R. Okay, alpha is in R only, so we are talking about R only. So f comma g or G comma F, both are the same thing. That is a symmetry. Okay, right. Now we say that, so we say that F is orthogonal to G if the inner product is 0. So whether you say F is orthogonal to G or G is orthogonal to F, both are the same thing, because F comma G is same as G comma F. Okay, and we write F is perpendicular to G. Now we want to now recall the Gauss-Schmidt process now. So we are going to apply the Schmidt process. So which actually identify with the given function. So let's say functions are f naught of x is equals to 1. Second function is f1 of x is equals to x. Third function is f2 of x is equals to x squared. Okay, right? Now, right? So now if I go back and mention you here, if you look at here in these two conditions, these are if and only if. So W is also a polynomial, so these are continuous functions over the interval, closed interval AB. So what it says is Wx is orthogonal to constant function 1, the constant function 1. And also Wx is orthogonal to the function, identity function. Okay, I of x is equals to x. Okay, right. So we are going to come back here. So with this Gauss-Schmidt process. Right. So now we have f0, f1, and f2. Now we want to determine the G0, G1, and G2, so that you take any two distinct pair, the inner product between them is 0, means they are orthogonal to each other. More than it is whenever you take that vector, or you can say this function G1, and if you take the inner product with itself, so that inner product value will be 1. Okay, so what we are trying to identify, G and G0, G1, G2 such that Gi comma Gj is equals to direct delta function, means is equals to 1 if I is equals to j, and 0 if I is not equals to z. So we try to identify this. So now by using the given set of functions. Okay, now we define G0 of x is equals to f0 of x divided by its norm, which is nothing but the induced norm. If you recall from your inner product spaces, induced norm is given by square root of this f comma f. Because you know that f comma f is if you take inner product with f with itself, it's always greater than equals to 0 non-negative. Then you can always take the square root, and this certainly satisfies all the properties of the non-linear space. Norm. Okay, and for specific reasons, so we are going to define a suffix to norm. Now it's very clear that when you take the norm of G0 by using the norm property, that's going to be norm of f0 by norm of f0, that's going to be 1. So very clearly you can see that norm of G0 is 1, because you are dividing the function by its norm itself. Now what will be this value G0 is now, so Z0 of x is equals to f naught of x divided by norm of f naught, 2 norm. So 2 norm of f naught is going to be square root of, so take square on this side, f naught comma f naught over the interval a to b, so integration a to b, f naught of x into f naught of x, that is f naught square x, so that is f naught is 1, so 1 dx, so that is going to be b minus a. Now see, now we are going to make some alteration here. Instead of working on general interval a to b, we are going to work over the interval -1 to 1. Okay, and then we later on we will going to generalize this to the result to the interval a to b. Okay, this has some specific reason why we have chosen -1 to 1 only. Why not 2 to 3 or 3 to 4 or and -2 to 2 and so on. Okay, this has some specific reason. So we are going to work now. Let this AB is going to be interval -1 comma 1. You will soon realize, once we will add here, you will soon realize why we have chosen specifically -1 to 1. Then this norm of f naught to square is 1 minus -1, that is 2. So this will implies norm of f naught is equals to square root of 2. This will implies g naught of x is equals to f naught, that is 1 by root 2. Okay, right. Now, what next here is, now we are going to identify the G1. Now, G1 of x. So, how will we define? So, instead of G1, first we will find the orthogonal element. Then we will make it divide by. So, norm of G1 is going to be something divided by something. Okay, so let's say this is going to be R1 of x and this is divided by norm of 2R1. What is R1? R1 is such that R1 comma Z0 is 0. We need to find G1 is such that G1 is perpendicular to G0 by using F1. Okay, by using F1. So, what will be the definition of R1 of x? If you recall from your linear algebra classes, so that is going to be F1 of x, and then you are eliminating the component in the direction of G0 from the F1. So that's going to be F1 comma G0 and G0 of x. Now you can verify that R1 comma Z0 is 0. Okay, so you can verify that. So now, so R1 comma Z0, if you specifically take the inner product. So R1 is what? F1 minus F1 comma Z0, so that is equals to F1 minus F1 comma G0 comma G0. Now use the linear property, that is going to be F1 comma G0. So F1 with Z0, then minus will be out. You have F1 comma Z0 times Z0 comma G0. Okay, right. So write it. So this is going to be using the linear property. Now, since this is a scalar, it will be out. So this is going to be F1 comma Z0 minus the F1 comma G0 will be out. So that is F1 comma Z0. So let me go to the next slide. So what we got us is R1 comma G0 was F1 comma G0 minus F1 comma G0 G0, this is Z0 by using the inner product property. So this is equals to F1 comma Z0 minus the scalar is out, so that is going to be F1 comma G0, and what is remaining is G0 comma Z0. Now since Z0 is such that norm of Z0, this is nothing but norm of Z0 to square, but you know that norm of G02 is equals to 1, so its square is also 1. Okay, so this is value is 1, so you will F1 Z0 minus F1 Z0 will get cancelled, so it's going to be 0. So your G1 of X is equals to R1 of X by norm of R1. Okay, so you have to, so for this now you can identify what is now this is equals to what. So for doing this you require R1. R1 is what? F1 minus F1 comma G0 G0. So for this now F1 comma G0, what is this? Is going to be minus 1 to 1 F1 of X times G0 of X dx. So that is equals to integration minus 1 to 1. So G0 was 1 by root 2. So 1 by root 2. F1 of X is X dx. So it's an odd function over the interval minus 1 to 1, continuous function and odd function. So definite integral property will lead you to 0. So this will implies R1 is nothing but F1 of X only. So because the right hand side, this quantity, this entry, this is 0. So only remaining with F1, and what is that is X. So now you can find what is norm of R1 cube is equals to integration minus 1 to 1 X square dx. So that is equals to 2 times integration 0 to 1 X square dx is the definite integral property. So you have 2 by 3. So this implies norm of R1. 2 norm is square root of 2 by 3. So you can write now G1. So what is G1 now? This implies G1 of X is equals to square root of 3 by 2 times R1, that is X. Square root of 3 by 2x, because it is in the denominator. Okay, right. Now we are in the position for getting the G2. So for finding G2, you are going to define R2. That is going to be F2 of X minus its component in the direction of Z0 as well as in the direction of G1. So minus F2 comma Z0 of X minus F2 comma G1 of X. So now I left it to you to prove that R2 comma G0. So you can verify. Okay, verify that R2 comma G0 equals to 0 and R2 comma G1 is also equals to 0. You use the similar split scalar properties of you use the properties of inner product space. Okay, right. Now let's determine this. So now what is F2 comma G0? That is going to be integration minus 1 to 1 F2 of X times G0 of X. So G0 of X was 1 by root 2 X square dx. So that is equals to 1 by root 2 times 2 integration 0 to 1 X square dx. So that is equals to 2 by 3. So what is there is square root of 2 by 3. Right? Yeah. Okay. Square root of 2 by 3. Now, what is F2 comma G1? That is equals to integration minus 1 to 1 x square into root 3 by 2x, so root 3 by 2 is out, x cube dx. But since x cube is a continuous function over the interval and it is odd, it's going to be 0. So what is R2 of x now? So this will implies R2 of x is equals to x square minus f2 comma j0 is square root of 2 by 3 into g0 of x is 1 by root 2 minus 1 by 3 and then 0. So x square minus 1 by 3. And now from here you can also determine what is norm of R2. So that let's say some alpha. Okay, let's say some alpha. So what it implies is G2, or you can say 1 by alpha. Okay, so G2 of x is equals to alpha time x square minus 1 by 3. Right, now see, G2 of x is alpha time x square minus 1 by 3. You have alpha time, you can write it as x minus 1 by root 3 into x plus 1 by root 3. Okay, so this equation, if you put equals to 0, so now very clearly G2 is orthogonal to G0 and G2 is also orthogonal to G0. Means you have G2 of x integration minus 1 to 1, G2 of x time G1. G1 is what? X time constant times, so square root of you can say it's what 3 by 2 x dx is 0, and integration minus 1 to 1 by root 2 G2 of x dx is 0. And this gives you two distinct roots. You have x naught, you can choose minus 1 by root 3, and x1 is 1 by root 3. And that's what, so you choose G2 of x. Okay, the roots of G2 of x as x0 and x1. Okay, and that will give you, so you see, this constant will not make any difference. So this alpha value, it's not need to be determined. Okay, right now. Okay, we don't require this. We require only the roots of this polynomial, and they are going to be distinct. Now, if you look at back in your calculus classes, and these polynomials are nothing but the Legendre polynomials. What you have obtained, so the obtained polynomials are Legendre polynomials, right, over the interval minus 1 to 1, p and x. If you go back and check, these are nothing but the these are obtained polynomial. Okay, and this has property that whenever polynomial, so each polynomial has distinct root minus 1 to 1. Okay, there will not be any repeated root. This will solve our problem. Okay, and we should able to identify the roots of this. And now we are in the position of defining the Gauss 2.0. So we choose x naught equals to minus 1 by root 3 and x1 is equals to 1 by root 3. Okay, in in case n equals to 1 on interval minus 1 to 1. So what you will have is integration minus 1 to 1 f of x dx is f of 1 by root 3 plus f of minus 1 by root 3 what is a W naught and W naught and W1 values. So W naught plus a W1, if you look at back, it is going to be 2, right? So this is going to be 1 plus 1 is 2. Okay, so that's if you take f is a constant, f is equals to 1, it matches. So W naught and W1 values are equals to 1. Okay, and if you go back and check summation of Wi, I is equals to 0 to n, that is going to be b minus a, the length of the interval. So here is the length of the interval is 2, so you can choose W0 and W1 as 1. Okay, right. So here this rule is known as a Gauss 2-point rule. So in the next session, we are going to address the error. The second thing, we are going to address how we will map this to the general interval a to b. Okay, so these two things, and then at the end we are going to look at the convergence of this Gauss 2-point rule or general rules. Okay, right. Okay, thank you.